Okay, so this is a video on the fats and oils topic, which continues on from when you just finished carboxylic acids and then esters. So if we have a look at, first of all, general structure of a fat and oil. So these are what we call naturally occurring, and they're triesters. Now what a triester means, and you can see hopefully now why this has been tabbed onto the back of the carboxylic acids topic and onto the end of the esters topic, because we're moving into triesters. Okay, now they are more generally known as triglycerides, and they're all esters of exactly the same alcohol. So whereas previously we looked at esters which are made from carboxylic acids and various different alcohols, this time the alcohol is common to all triglycerides. That alcohol, you need to know the name of it and you need to be able to draw it, but we'll look at that in a minute. It's called propane 1,2,3 triol. Now please, when you're writing the name of this, don't forget the E at the end here, and don't forget the hyphens as well. That is commonly known as glycerol. It's a very sort of viscous alcohol because it's a fairly short chain with 3 OH groups, gives it fairly significant hydrogen bonding throughout and makes it very viscous. Now the difference between this and other esters is, of course, you've got a carboxylic acid with 3 OH groups, and you can maybe start to see why it's called a triester, because each of those OH groups can actually form an ester linkage or an ester bond, meaning that it has 3 ester bonds per propane 1,2,3 triol molecule, making it, as we said, a triester. Now the difference here is it's always attached to 3 very long chain carboxylic acids or organic acids. They tend to be between 16 and about 20 carbons, so much longer than the ones that we've looked at in the last topic. And they're called fatty acids. So we're getting into very much biochemistry and the biology of chemical compounds here and esters. Okay, so there's our propane 1,2,3 triol called glycerol. You need to be able to recognize it. You need to be able to name it, both the glycerol word and the propane 1,2,3 triol, and you will also have to be able to draw it. That reacts with 3 carboxylic acids, very long chain carboxylic acids, where N is between 14 and 18, but nonetheless carboxylic acids. You can see the COOH group on that. So that's no different than the esters that we looked at in our last topic. And where you need to be careful here is in this COH group, you need to, I suppose, turn around 180 degrees there to see how it lines up with my OH. And then exactly the same happens as has happened in all our esterification reactions. The H from the alcohol has been removed, the OH from the carboxylic acid is removed, and then we get that O from the alcohol which is left over, forming the new bond with the COO bond of the carboxylic, the carboxylic acid group. Now, instead of having 3 independent fatty acids or carboxylic acids here, I now have those fatty acid chains attached to the 3 OH groups of the propane 1,2,3 triol, and now I just have one molecule. And this molecule here is called a triglyceride, a triester, because we have 3 ester groups in it, but commonly called a triglyceride. And we get 1 water molecule per ester group, exactly the same as we got when we did our esters previously. Okay, now your triglycerides can occur as either fats or they can occur as oils. The only difference between fats and oils is that a fat is solid at room temperature, has a higher melting point, and an oil is a liquid at room temperature. The fatty acid molecules within a fat tend to be saturated. The fatty acid molecules within an oil tend to be unsaturated, and this impacts upon the melting point of those substances. So I want you to have a go at the questions as we go through, so I'll bring up the question. If you could pause the video, do them, and keep your answers, and we'll check those when we get back to school. Okay, so why do the oils have slightly lower melting points than our fats? Well, I said earlier that it was because of saturation versus unsaturation. So we can see here, this is a very saturated palmitic acid, and it forms a triglyceride like so. And what you can see here is that these triglyceride, the fatty acid parts of it, lie very close together. Now you guys should know by now that that will increase the van der Waals forces of attraction. The unsaturated fatty acids form triglycerides, which have more kinking, more bending, and that means that the fatty acid chains lie much further apart, and therefore that decreases the strength of the van der Waals forces in there, making these things have a much lower melting point than you might anticipate. So it's an argument that we've come across before, but it's an argument that you need to be able to apply to triglycerides on this particular occasion. So those are the reasons there, just what I spoke about. Okay, so you have a variety of different types of fatty acids that you need to be aware of. We've got saturated ones, which have got no carbon-carbon double bonds in them at all. Don't count this as anything to do with unsaturation. It's to do with carbon-carbon double bonds, not to do with other double bonds like carbon-oxygen double bonds. We have some unsaturated ones here. Okay, this one in particular is called oleic acid. This is what we would call mono unsaturated, so there is one carbon-carbon double bond per fatty acid molecule. And then we have down here, we have got our poly unsaturated molecules. This is one called linoleic acid. And poly just means there's more than one carbon-carbon double bond. We can see fairly obviously there's a couple of carbon-carbon double bonds in that. So just a bit of terminology there: saturated, mono unsaturated, and poly unsaturated. Now, we can harden these oils, and hardening oils means basically turning them from a liquid into a solid. We've done this chemistry at AS level. So this is where we take our hydrogenation of a carbon-carbon double bond with our platinum or nickel catalyst at about 4 atmospheres, 170 degrees Celsius, give or take a bit. And this increases the proximity now of these fatty acid chains to each other. So originally, if we look at the diagram on the right hand side, here we can see a double bond. Once we hydrogenate that double bond, you can see now that the linear structure of the molecule is, well, it's much more linear than it was previously when it had the double bond in there. Okay, so with the increase of hydrogenation and making that fatty acid molecule a little bit linear, you increase the melting point. Not so much that you add more electrons and increase the van der Waals forces that way, but just the fact that these molecules can now pack more closely together, and that increases the van der Waals forces and increases the energy needed to overcome them, and therefore increases the melting point. Okay, so there's some more questions. If you can pause the video and have a go at them. Okay, so drawn fatty acids in a cis-trans formation. This can often be or present a little bit of a challenge to students. Well, if it's a saturated fat, it really isn't a big deal. Okay, if it's a cis unsaturated fat, okay, then if we look here at the carbon-carbon double bond that was within the molecule, you can see the two hydrogens are on the same side of it. So if you're asked to draw it in a cis formation, okay, or a Z formation, that would be the formation that you would be looking to present to the examiner. Whether you're around your carbon-carbon double bond, you have your two hydrogens on the same plane. If we went to the trans formation or the E formation, you can see now that we do the double bond out in exactly the same way as again, but we have our hydrogens on opposite sides of the double bond. So just make sure that you are able to draw structures that are in either the cis or the trans formation for your unsaturated fatty acids. Okay, there's another question 3 and 4. If you can pause the video and have a go at those. Again, pause the video. And there's a little bit of text missing off the bottom of that. That says, I'll just put it in there, was an oil or fat at 25 degrees Celsius. Okay, pause the video. Pause the video. Pause the video. Okay, let's look now at saponification of these triglycerides. This is essentially parallel to alkaline hydrolysis that we did previously with our esters. So it's usually done with triglycerides, okay, with sodium or potassium hydroxide. Okay, and the products that we get then are the original alcohol and the fatty acid salt. That will depend on whether we use sodium or potassium hydroxide. But this is exactly what we did whenever we did alkaline hydrolysis of our esters previously. The reason why this is called saponification is because that fat, that fatty acid salt molecule there is used in soap, is a molecule in soap. So this is a generic equation for saponification which you'll need to apply to whatever the examiner gives me. Now, if you did ask you for a balanced symbol equation, you would have to have 3 sodium or 3 potassium hydroxide. Read the question carefully, make sure you don't put the wrong hydroxide in. Okay, the R group, okay, so if it's, I don't know, C17H35, let's say, well then your salt of your carboxylic acid will of course be C17H35. Okay, and that would be the same the whole way down. Okay, remember, do not put a bond in between the oxygen and the sodium. It's not there, it's not a covalent bond. And you can put the charges in if you want. But you can see you get glycerol back and you get the very long chain fatty acid salt of the fatty acid. So there's a question there which you can have a go at if you pause the video and have a go at that. There's another one if you pause the video. Another one. That's maybe missing off. That's just C17H35, and there's a hydrogen down the bottom of the screen there. It's maybe missing off that one as well. Pause the video again. Pause the video again. Pause the video again. Pause the video again. Pause the video. Okay, let's look then at transesterification. So we've looked at lots of esterification reactions there, and we're now going to look at what we call transesterification. So this generally involves taking an ester this time and reacting with an alcohol and getting a new ester and a new alcohol. So the reason for doing it would be we're after esters that have different properties than the ester that we have at the minute. So more desirable properties, maybe better at combusting, maybe it's less viscous, maybe it has a lower melting point or lower boiling point. But we're trying to change the properties of the ester and make a more useful product with different physical properties. So if we look at the generic formula of an ester there on the left and the generic formula of an alcohol, you'll see in transesterification here you have basically swapped the groups. Trans meaning across from, so we have swapped these two groups here, hence the term trans. We've still made a new ester here, hence the term esterification. So the conditions you need to know for this are heat, and your catalyst is sodium hydroxide. You can use sodium methoxide if you want, but sodium hydroxide is fine. So if maybe you could predict, you see an example at the bottom, maybe you could predict the structure of that and pause the video and then I'll pop the answer up. Okay, so you get the methyl group swapping with the ethyl group there. Okay, so you can see we've gone having the CH3 there. Okay, we've got rid of the C2H5 and we've shortened the length of that ester, making it probably a slightly lower melting point, lower boiling point, a bit more volatile, probably a bit more flammable. So this is used in two specific areas in your syllabus. Biodiesel, which is whenever you're trying to produce a mixture of methyl and ethyl esters of fatty acids, and that's made from transesterification of natural fats. So this is basically making biodiesel from oil, okay, and fats. So it might be just simply chip pan oil. Okay, waste from restaurants, waste from your local chip shop. So you've got a renewable resource here which can be used to power cars and that are adapted to run on biodiesel. Okay, so as I've said in there, you can use rapeseed oil in a reaction with methanol. So the good thing about it is indeed it leads to a slightly more sustainable process because we're using renewable resources. It has a zero net carbon dioxide emission. What that means is when the plants, the rapeseed plants, or if it's sunflower oil, are being grown, they will of course through photosynthesis take in some carbon dioxide. When you burn them as biodiesel, they will give out carbon dioxide, but they only can give out the amount of carbon dioxide that they have taken in. So there's a net zero carbon dioxide emissions, unlike fossil fuels and coal and natural gas, etc., petrol, diesel, especially in this context. You don't have any pollutants, so sulfur dioxide isn't made, which is made when you burn diesel and you burn petrol in cars. There's small amounts of sulfur in there to give you sulfur dioxide, which you would hopefully recognize as giving you eventually some sulfuric acid, some acid rain. So let's have a look at what goes on. There's my general triester. So I've got That's between sort of 16 and 18 carbons long, that chain. I reacted with 3 ROHs. Remember we said earlier that the ROH, the alcohol used, was either ethanol or methanol. That's the type of esters that we're trying to produce here. So the R will be a C2H5 or a CH3 group. So we heat it again with sodium hydroxide. Okay, and we get our new biodiesel molecule. Now what's the difference? Well, if we look on the left, this molecule is one big molecule. So what I've done is I've broken the bonds, and I've now created 3 separate biodiesel molecules. Okay, they're much smaller, they have much weaker van der Waals forces, they're much more volatile, they're much less viscous. Okay, they burn easier. Okay, so they flow through a car engine much more easily, and they produce a consistency and a energy output similar to that of diesel. So there's a question. Just pause the video and have a go at it. Again, pause the video, have a go at it. This bottom acid here, by the way, is called linoleic acid. Again, pause the video, have a go at the question. Okay, final one then is intermolecular transesterification used to make margarines. So this is when we take a mixture of esters, okay, again, and we use our sodium hydroxide enzyme, but this time instead of an ester and an alcohol, we have an ester and an ester, and we're swapping groups within one ester and another used to make soft margarines. So you can see there, okay, we've gone from having R1 with R2 to having R2 with R3. Okay, so we're swapping our ester groups, and again we're doing it to change the properties of our esters, this time to make soft margarine. It involves making another way of making margarine, which is hydrogenation of unsaturated fats. Okay, and that makes what we call trans fatty acids, which are fairly detrimental to health. They cause build-up of cholesterol and eventually leading to strokes and heart disease and stuff like that. So this is a different method, and hopefully a more biologically and health safe method than so let's have a look at what happens here. Let's take a fully saturated solid fat at room temperature. Let's take an unsaturated triglyceride oil. Okay, let's transesterify them and see what we get. So when I do that, when I transesterify, I do exactly that. I swap groups. In this instance, I have swapped that for that. And now here I've got a bit of more unsaturation, so instead of being really solid, I've reduced the melting point. So it's a more liquid, softer. Okay, here, instead of being a liquid, so loads of unsaturation and very weak van der Waals, I've increased the saturation, so I've increased the melting point and turned this into a softish solid. So I get a mixture of the old and the new, everything's in there, but the whole point of it is that the consistency of this now, instead of having a very solid fat and a very liquid oil, the consistency of this is now one of soft margarine. And we can add colours and vitamins and flavours to it to sell it to the consumer. Okay, the last one then we have intramolecular. So the other one was intermolecular. If you just go back, we're swapping it between different molecules of ester. Here, intramolecular, same sort of principle, but we just switch the ester group around in the molecule. And again, that changes the intermolecular attraction, changes the properties of that particular ester. Okay, so there's a question on the board which you could pause the video and have a go at. There's another one. Okay, and that's the end. Okay guys, hopefully that was useful and takes you through your fats and oils and esters topic, and you do the questions and mark them and check them, and I will send you the answers to those so you can do so.